So we have what? Last time we got the formula cosine theta equals u dot product v and the u divided by v. Okay. And then now definition of orthogonal vectors. Two vectors u and v in R and are orthogonal when dot product u dot v equals 0. Okay, that's the definition. If u dot product v equals 0, that means they are orthogonal vectors. Okay, orthogonal vectors. So let's take a look how to get this property. Okay, so we know if two vectors are orthogonal, that means these two are perpendicular. That means the angle between these two vectors is going to be 90 degree. So we can see from this formula, theta equals 90 degree. Okay. Since theta equals 90 degree, that means cosine theta 90 degree equals 0, right? So we're gonna get these two equals 0. Okay, times these two from both sides, so we're gonna get dot product equals 0. So we can derive the formula from here, right? From here. So that's the property of orthogonal vectors. Now, I'm gonna give you guys 1 minute to try this example. Check. U equals 1, 0, 0, 0, and V 0, 1, 0. Check whether these two vectors are orthogonal or not. Orthogonal or not. Okay, try it by yourself. 1 minute. Okay, now let me try it. So check whether this guy are orthogonal. We just need to use this formula, right? U dot V 1, 0, 0 dot 0.10. So I mean 1 dot 0, 0 times 1, 0 times 1. And you're gonna get 0, right? So U and V are orthogonal. Okay, orthogonal. Okay, let's continue. Theorem. Five point five. The triangle inequality. Triangle inequality. If U and V are vectors in Rn, then we have this property. Okay, we have these properties. Okay, and another theorem. 5.6. The Pythagorean theorem. Pythagorean theorem. If U vector U and the vector V are vectors in Rn, then U and V are orthogonal. If, only if, we have U plus V square and U square plus V square. Okay, and we have matrix. Okay, also we can use matrix form to express that the vector. So for example, if I give you U1, U2, we always can write down U1, U2, blah, 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 UN. Okay. And if we have V vector, we always can write down as V1, V2, blah, 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 Vn. Okay. And of course, you guys can write down the way for dot product. For dot product, you can write it as this way, like that. U transpose, okay? U transpose times V. If we write down as the matrix form, because this is a matrix form for the U is a column, right? If you transpose it, you're going to get the row. And the V is V1, V2. And this guy will boil down to the U1, V1 plus U2, V2. Okay, that's it. So that's the inner product. And we use the matrix form to express the inner product. Of course, now I'm gonna give you guys an example. Let you guys try it. For example, I give you a vector u equals 2 and 0, and v is 3, 1. Use the matrix form to calculate the dot product. Try it by yourself. Use the matrix form. Okay, matrix form gonna be what? Like that. All right. So dot product gonna change, becomes u transpose times v. Okay. Okay, let me write down the answer for you guys. So for this one, in the product, we have what? We have u dot v gonna be a u transpose v. That's gonna be a 2, 0. 2, 0. 3, 1. So 2 times 3, 0 times 1 equals 6. Okay, that's it. That's it. Okay, so we wrapped up the chapter 5. Now we're gonna go to chapter 7. Chapter 7. Eigenvalues and Eigenvectors. Okay. Eigenvalues and Eigenvectors. Definition. Of eigenvalues and eigenvectors. Let A be an n times n matrix. The scalar lambda is the lambda is an eigenvalue of A when there is a non-zero vector x such that AX equals lambda X. The vector X is an eigenvector of A corresponding to lambda. Corresponding to lambda. Okay, corresponding to lambda. Okay, now let's take a look at the definition. The definition we defined, if we found a matrix times X equals lambda times X vector, we called this lambda is eigenvalue, and the X vector is eigenvector. Okay, the X vector is eigenvector. If we have such expression, AX squared, AX equals lambda X. Okay, here the X is a vector. Okay, lambda is a scalar. We call lambda is eigenvalue. X is the eigenvector. Okay, now that's the definition. Now let's take a look. For the matrix A equals 2, 0, 0, negative 1. Okay, 0, negative 1. Verify that x1, 1, 0 is an eigenvector of A corresponding to the eigenvalue lambda 1 equals 2. Okay, and that x2, 0, 1 is an eigenvector of A corresponding to the eigenvalue negative 1. Okay, negative 1. Okay, so how to verify? Just plug in this formula. AX equals lambda X. We check AX1 whether that equals lambda 1 times X1. All right, check this formula, whether this formula is satisfied. Okay, now let's take a look. AX1, that is what? 2, 0, 0, negative 1 times x1. x1 can be written down as matrix form. Okay, matrix form. That is, we can get, that is 2, 0, right? And we can say lambda 1, x1 equals what? Lambda 1 is 2, right? We can find that is 2, 0, right? So we can see ax1 equals lambda 1 x1. Okay, so that means that is we verify that lambda 1 is eigenvalue, x1 is the eigenvector. Okay, now very similar. Try the lambda 2 and the x2. Okay, try the x2 vector. Try it by yourself. I give you guys 1 minute. Okay, now I'm gonna write down the answer. So the first thing we calculate what? We calculate this guy. ax2 to 0, 0, -1, 0, 1, right? Then you're gonna get what? You're gonna get 0, -1. Okay, and of course you can calculate lambda 2 times x2. Lambda 2 is -1, right? -1 times x2 is 0, 1, and you're gonna get 0, -1. That's it. That's it. Okay. So we just verify that ax2 equals lambda 2 x2. Okay. So that's the definition. Now I'm gonna here there's a verification. So if I give you a matrix, how to find eigenvalue and eigenvector? That's a way. That is a way. Okay. Let me give you guys the theorem firstly. Seven point two eigenvalues and eigenvectors of a matrix of a matrix. Let A be an n times n matrix. Okay. Now an eigenvalue of A is a scalar lambda such that the determinant lambda I minus A equals 0. Okay, so that's the first important properties. If I give you a matrix, you can try this formula to calculate the eigenvalue. Okay, now 2. The eigenvectors of A corresponding to lambda are the non-zero solutions of lambda I times A. Okay, so how to find the eigenvectors? We're gonna use this formula, lambda I minus A. Okay, now the equation determinant lambda I minus A equals 0 is the characteristic equation of A. Moreover, when expanded to polynomial form, the polynomial is what? It's lambda I minus A. That can be written down as lambda n say n minus 1, lambda n minus 1, C2, lambda 2, C1, lambda plus C0. Okay, is the characteristic polynomial of A. Characteristic polynomial of A. Okay, so that's the property. And then now let's take a look at an example how to find the eigenvalues and corresponding to eigenvectors. Okay, now let's take a look. The first example. Find the eigenvalues and corresponding eigenvectors. Of A is what? Is 2, -12, 1, -5. 1, -5. So how to find the eigenvalues? We have what? We use the formula here. Determinant of this guy equals 0 to find the eigenvalues. Let's take a look. So we have lambda I minus A. Alright, and then we can write that as lambda 1, 0, 0, 1 identity matrix. Right, and then we have lambda 0, 0, lambda subtraction. And again, you can get what? Get simplified lambda plus 5. Okay. And how to calculate the determinant of this guy? You're gonna get what? You're gonna get lambda minus 2, lambda plus 5, subtract -1 times 12. You're gonna get what? You get distribution. You're gonna get okay. So we let this guy equals 0. Okay, we let the whole thing equals 0. Try to solve the lambda. Okay, lambda. So we can use factoring method. Okay, factoring method. And you can solve this guy when the first solution is -1 or second solution is -2. Okay, we have two solutions. One is -1, another one is -2. Okay, very good. Now we get the two eigenvalues, right? Two eigenvalues. Two eigenvalues. Now we need to find the eigenvectors. So for the first eigenvalues, okay, and in order to find the eigenvectors, we need to plug in this formula, right? So lambda 1I minus A x, right? This guy. Well, what are we gonna get? We're gonna get lambda 1I minus A. That is what? That is this guy equals to lambda 1. Lambda 1 is -1. You plug in here. So plug in here because lambda I minus A we already calculated. The matrix is like that, right? So if lambda 1 equals -1, you just plug in the -1 here. You gotta get the matrix -3, 12, -1, -1 is 4, right? 4. And so now we let x vector, we have two elements, right? That equals 0 or 0 vector, because we want what? We want this the whole thing equal to 0 vector. Okay, equals 0 vector. So that is the lambda I minus a, we got this one, and x vector is that is x1, x2 equals 0 vector, gonna be this guy 0, 0. Okay. Now, then we can solve it. Solve the x1 and x2. What are we gonna do? We use Gauss-Jordan elimination, right? We learned before. We can use Gauss-Jordan elimination. Okay, and then we can Gauss-Jordan elimination. And then we're gonna get what? Okay, and then what are we gonna get? We're gonna get x1 minus 4x2 equals 0, right? So we can get x1 equals 4x2, right? If we use parametric representation, we let x2 equals t, then x1 equals 4t, okay? And then we can write down the x vector can be 4t or t, right? And the t for 1, t doesn't equal 0, okay? So we, from this solution, we can say t can be any real number except t doesn't equal 0, okay? So we have infinity solution for the eigenvector. Okay, we have infinity solution for eigenvector. The eigenvector can be written as this one. Okay. We have unique solution for the eigenvalue. However, for each eigenvalue, we can have infinity eigen vector. Okay, eigenvector. So now similarly, for the second eigenvalue, if lambda 2 equals -2. You can try it by yourself. Okay, you can try it by yourself. Find the eigenvector for me. So basically, you're gonna follow this formula, right? Let this guy here is lambda 2. Okay, here lambda 1. Now we're gonna calculate the lambda 2. I minus a times x. Okay, lambda 2. That means we're gonna plug in the lambda 2 here, right? Lambda 2. After plugging lambda 2, you're gonna get this matrix. Try it by yourself. Okay, guys, I'm gonna give you guys finish these problems. Let me do it on board. So for this guy, lambda 2I minus a x. So what do we have? Because lambda 2 is -2, so we just plug in the -2 here, right? Because lambda I minus a, so now it's lambda 2I minus a. We're gonna get the matrix that is -4, 12, 3. Okay, and x1, x2 equals 0 vector. And again, you can solve it. So we have what? We use the Gauss-Jordan elimination. Gauss-Jordan elimination. And this guy will boils down to the what? We'll give you 1, -3, 0, 0, 0. So x1, I mean x1 equals 3x2. Right? We let x2 equals 2. That means the vector and equals t, 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 3, 1, and t doesn't equal 0. Okay, t doesn't equal 0. Okay, so here we just have one parameters. One parameters. We can see here for the eigenvector, we have just one parameters. So we can say this eigenspace, the dimension of the eigenspace is 1. The dimension of the of its eigenspace is 1. Okay, and we can see here is the dimension of the eigenspace is 1. Okay, eigenspace is 1. That's it. That's it. Now let's try the last example. Find the eigenvectors and eigenvalues for me. So eigenvalue, eigenvector, and also the dimension of the eigenspace. Dimension of eigenspace. Try it by yourself. Okay. Okay, now let me write down the answer on board. So the first thing, we're gonna calculate the eigenvalues. Right? So eigenvalue, we're gonna get lambda, lambda I minus A minus and this guy will boils down to the okay, and the determinant of this triangular matrix gonna be the diagonal multiply the diagonals, right, equals 0. So you can find the eigenvalue is 2. Okay, so after you find the eigenvalues, then you can use the formula to find the eigenvector. Right? Now plugging in the lambda 2 to here, right? Lambda 2 to here, you're gonna get lambda I minus A 0, -1, 0, 0, 0, 0, 0, 0, 0. Okay, I think here is a very special case because we found a bunch of 0, and then we don't need to use the Gauss-Jordan elimination, right? We just find the solution times x1 -1. So we found x2 equals 0. Right? X2 equals 0. Okay, we only found that x2 equals 0. So how to find the solution? We just let, for example, s equals x1 equals s, x3 equals t. Okay, that means what? The vector x can be write down as x1, x2, x3. We find S0t, okay, S0t. And of course, you can write down it this way. Spread the S and T. So S is in the first element. You can find 1, 0, 0. T is in the last element or last row. Write down is that. Okay. So now the eigenvector can be expressed as like that. And we see here S and T, we have two parametric or two parameters, S and T. So that means the dimension of the eigen space is 2. Right? It's 2. That's it. That's it. I'm gonna wrap it up class here. Thank you for coming. Have a nice day. Okay, so please start your homework as early as possible. Okay, homework 6. Okay.